You wake up tomorrow, but something's wrong. You're not in your bed. You're standing in ancient Rome, and someone just handed you the blueprints for the Pantheon. Your job: build a concrete dome that will last 2,000 years using only tools and materials available in 126 AD. Oh, and make sure it's earthquake-proof. Good luck. You're going to need it. Hey everyone. Tonight we begin with a journey through time to explore three engineering achievements that continue to baffle modern science. From the impossible precision of the Great Pyramid to the mysterious strength of Damascus steel, we'll discover how ancient civilizations accomplished feats that we still struggle to understand today. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments where you're tuning in from and what time it is for you. It's always fascinating to see who's joining us from around the world. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey through the greatest engineering mysteries of the ancient world. The morning sun rises over the Giza Plateau, casting long shadows across the desert sands. Before you stands what many consider the greatest engineering achievement in human history: the Great Pyramid of Khufu. Built around 2580 BC, this monument has stood for over 4,500 years, and despite decades of research, archaeologists and engineers still can't agree on how it was actually constructed. Let's start with the numbers, because they're staggering. The Great Pyramid originally stood 481 feet tall. That's about 50 stories high. Its base covers 13 acres, roughly the size of 7 football fields. The entire structure contains approximately 2.3 million stone blocks, each weighing between 2.5 and 15 tons. That's equivalent to building a monument out of 6,000 modern cars, except these cars are made of solid limestone and granite. But here's where things get truly mind-boggling. The pyramid wasn't just big, it was precise. The base is level to within just 2.1 centimeters. To put that in perspective, if you built a square the size of a football field and wanted to achieve the same level of accuracy, you'd need to ensure that no corner was more than an inch higher or lower than any other corner. The ancient Egyptians did this across 13 acres of desert sand using Bronze Age tools. The alignment is equally impressive. The Great Pyramid is oriented to true north with an accuracy of just 3/60ths of a degree. That's more precise than the Greenwich Observatory in London, which is off by 9/60ths of a degree. How did ancient Egyptian engineers, working 4,500 years ago, achieve this level of astronomical precision? Modern engineers attempting to understand the pyramid's construction face a fundamental problem. The methods that should have been used simply don't work. For decades, archaeologists assumed that the Egyptians used ramps to move the massive stone blocks up the sides of the pyramid as it grew taller. It's a logical theory. After all, how else would you get a 15-ton block of granite 400 feet into the air? But when engineers tried to calculate what these ramps would need to look like, the theory began to fall apart. A straight ramp leading to the top of the pyramid would need to be over a mile long and would require more material than the pyramid itself. Zigzagging ramps wrapped around the pyramid's sides would work better, but would require constant dismantling and rebuilding as the pyramid grew taller. Internal ramps could solve some problems, but would create others. How do you build ramps inside a structure while you're still building the structure? The Japanese pyramid experiment of 1978 perfectly illustrates these challenges. Japanese engineers, determined to prove that pyramid construction was possible using ancient methods, attempted to build a scale model using traditional techniques. They had access to modern tools, transportation, and unlimited funding. Their goal was modest: a pyramid just 30 feet high, roughly 1/15 the height of the Great Pyramid. The results were humbling. After months of work, the Japanese team managed to construct a small, crooked pyramid that looked nothing like the precise monuments of Giza. They abandoned traditional methods partway through the project and resorted to modern cranes and machinery to complete even their modest structure. If experienced engineers with modern backup tools struggled to build a 30-foot pyramid, how did ancient Egyptians build one that was 480 feet tall? The stone cutting presents another mystery. The Great Pyramid contains granite blocks quarried at Aswan, 500 miles south of Giza. These blocks were cut with such precision that you can't slide a knife blade between the joints. Some blocks weigh over 70 tons, equivalent to about 50 modern cars. How did Bronze Age workers cut and shape granite with such accuracy? Modern stonemasons, even with diamond-tipped saws and precision equipment, struggle to achieve the tolerances found in the Great Pyramid. The ancient Egyptians supposedly did this with copper tools, wooden mallets, and stone hammers. Experimental archaeology has shown that these tools can cut limestone, but the process is incredibly slow and labor-intensive. Cutting a single large block to the precision found in the pyramid would take a team of skilled workers several weeks. But limestone was actually the easy part. The king's chamber inside the Great Pyramid is built entirely of granite, a much harder stone. The chamber contains massive granite blocks, some weighing over 50 tons, cut to tolerances measured in millimeters. The ceiling consists of 9 granite slabs, each weighing about 50 tons, arranged in a complex pattern that distributes the enormous weight of the pyramid above. Transportation presents yet another puzzle. Moving a 70-ton block of granite 500 miles from Aswan to Giza would be challenging even today. The Nile River provided a transportation route for part of the journey, but the granite still had to be quarried, moved to the river, loaded onto boats, transported north, unloaded, and then moved to the construction site. Ancient Egyptian boats were technological marvels in their own right, but they were built for cargo like grain and pottery, not 70-ton granite blocks. Loading such massive stones onto wooden boats without sinking them would require sophisticated engineering. Some researchers have suggested that the Egyptians built special barges specifically for transporting pyramid stones, but no remains of such vessels have ever been found. Once the stones reached Giza, they had to be moved from the Nile harbor to the construction site, then lifted hundreds of feet into the air and positioned with millimeter precision. The logistics are staggering. If the pyramid was built over a 20-year period, as most Egyptologists believe, the construction crews would have had to place one block every 2 to 3 minutes, working 10 hours a day, 365 days a year. Recent technological advances have revealed even more mysteries. Ground-penetrating radar and cosmic ray imaging have detected voids inside the Great Pyramid that weren't previously known to exist. These empty spaces suggest internal chambers or passages that serve no obvious purpose. Why would the pyramid's designers include these features? Were they part of the construction process, or do they serve some function we don't understand? The precision extends beyond individual blocks to the pyramid's overall geometry. The ratio of the pyramid's perimeter to its height is remarkably close to 2 pi, the mathematical constant pi. This could be coincidental, but many researchers find it unlikely that such a precise mathematical relationship would occur by accident in a structure this complex. The pyramid's internal passages and chambers also show remarkable engineering sophistication. The Grand Gallery, a sloping corridor leading to the king's chamber, features a corbelled ceiling that distributes weight away from the chamber below. The precision of the stonework in these internal spaces is even more impressive than the exterior, despite being hidden from view. Temperature control inside the pyramid appears to have been carefully planned. The internal temperature remains constant year-round at 68 degrees Fahrenheit, exactly the average temperature of the Earth. This thermal stability suggests that the pyramid's designers understood principles of thermal mass and air circulation that wouldn't be formally described by science for thousands of years. The construction workforce required for the pyramid represents another logistical challenge. Conservative estimates suggest that building the Great Pyramid would have required at least 20,000 workers, though some researchers believe the number could have been much higher. Feeding, housing, and organizing such a massive workforce in the desert would have required sophisticated planning and resources. Archaeological evidence suggests that the pyramid builders were well-fed, skilled workers, not slaves as commonly portrayed in popular culture. The workers' village near the pyramid contains evidence of a complex society with bakers, brewers, doctors, and administrators supporting the construction effort. This infrastructure would have been almost as challenging to organize as the pyramid construction itself. Tool technology presents another puzzle. The precision achieved in the pyramid's construction would be impressive even with modern steel tools, but the ancient Egyptians worked primarily with copper implements. Copper is a soft metal that dulls quickly when cutting stone. Maintaining the thousands of tools needed for pyramid construction would have required a sophisticated metallurgical industry and constant tool replacement. Some researchers have suggested that the Egyptians had access to harder metals or more advanced tool technology than traditionally believed. A few artifacts suggest possible knowledge of ironworking or even steel production, but such evidence remains controversial and isn't widely accepted by mainstream archaeology. The organizational challenges of pyramid construction may have been even more daunting than the technical ones. Coordinating thousands of workers, managing supply chains for materials and food, maintaining quality control, and keeping the project on schedule would have required administrative sophistication that rivals modern construction management. Recent computer modeling of pyramid construction has revealed just how precise the planning would have needed to be. Every stone had to be cut to exact specifications, delivered to the right location at the right time, and positioned correctly on the first attempt. There was no room for significant errors. A mistake in the lower courses would compound as the pyramid grew taller, potentially causing catastrophic structural failure. Weather patterns would have significantly impacted construction. The annual Nile flood lasted several months and would have shut down transportation of materials from Aswan. Construction planning would have had to account for these seasonal variations, stockpiling materials during favorable periods and adjusting work schedules accordingly. The pyramid's internal drainage system shows remarkable understanding of hydraulic engineering. Hidden channels prevent water from accumulating inside the structure, protecting the internal chambers from flood damage. These drainage features are invisible from the outside but demonstrate sophisticated planning for long-term preservation. Quality control throughout the construction process would have required skilled inspectors and standardized measurement systems. The consistency of the stonework suggests that quality standards were established and maintained throughout the decades-long construction period. This level of standardization indicates a highly organized construction management system. The mathematical knowledge required for pyramid construction far exceeded basic arithmetic. The builders needed to understand complex geometry, calculate angles and volumes, and solve engineering problems that would challenge modern professionals. This mathematical sophistication had to be maintained and transmitted throughout the construction period. As we step back from the Great Pyramid and consider everything we've discussed, one fact becomes clear. This monument represents an achievement that we still don't fully understand. The combination of precision, scale, and sophistication found in the pyramid exceeds what should have been possible with Bronze Age technology. Modern attempts to build pyramids using ancient methods have consistently failed to achieve even a fraction of the precision and scale found at Giza. The Japanese experiment demonstrated that even with modern backup support, constructing a pyramid using traditional methods is extraordinarily difficult. The Great Pyramid stands as a testament to human ingenuity and determination, but it also serves as a humbling reminder of how much we still don't know about our own history. The ancient Egyptians accomplished something that we, with all our modern technology and understanding, struggle to comprehend, let alone replicate. The mystery of the pyramid's construction continues to inspire researchers and engineers around the world. New technologies like 3D scanning, ground-penetrating radar, and artificial intelligence are providing fresh insights into ancient construction methods. But they're also revealing new mysteries and complexities. Perhaps the most important lesson from studying the Great Pyramid is that ancient peoples were far more sophisticated than we often give them credit for. The pyramid builders possessed knowledge, skills, and organizational capabilities that allowed them to achieve the seemingly impossible. Understanding how they did it might teach us something valuable about engineering, mathematics, and human potential. We leap forward in time now, from the sandy plateau of Giza to the bustling streets of ancient Rome. The year is 126 AD, and Emperor Hadrian has just commissioned the construction of the Pantheon, a temple that will feature the largest unreinforced concrete dome in the world. The engineers tasked with this project are about to create something that will outlast the empire itself, using a technology so advanced that we're only beginning to understand it today. Standing before the Pantheon in modern Rome, you're looking at a 1,900-year-old building that could probably survive another 1,900 years without major repairs. The massive concrete dome, 142 feet across and weighing over 4,500 tons, has endured earthquakes, floods, wars, and nearly 2 millennia of weather without cracking or collapsing. Modern concrete structures are designed to last 50 to 100 years before requiring major maintenance. What did the Romans know that we don't? The story of Roman concrete begins not with the Pantheon, but centuries earlier with volcanic ash and a discovery that would revolutionize construction. Around the 3rd century BC, Roman engineers began experimenting with a local volcanic ash called pozzolan, named after the town of Pozzuoli near Naples. When mixed with lime and water, this ash created a concrete that was not only strong but actually got stronger over time, especially when exposed to seawater. This was revolutionary. Before Roman concrete, most large structures were built using massive stone blocks held together with mortar or metal clamps. These construction methods required enormous amounts of skilled labor and perfectly fitted stones. Roman concrete allowed builders to create complex shapes, curved surfaces, and massive spans that would have been impossible with traditional masonry. But here's what makes Roman concrete truly extraordinary: it's self-healing. Modern engineers have discovered that Roman concrete contains tiny limestone clasts, small chunks of limestone that weren't fully dissolved during the mixing process. When cracks develop in the concrete over time, water seeps in and reacts with these limestone fragments, creating new calcium carbonate that fills the cracks automatically. This self-healing property means that Roman concrete structures actually repair themselves, becoming more durable over time rather than gradually deteriorating like modern concrete. It's a technology that seems almost magical, yet it was developed 2,000 years ago using materials and methods that we're only now beginning to understand. The Pantheon represents the pinnacle of Roman concrete technology. The dome is a masterpiece of engineering that demonstrates sophisticated understanding of materials science, structural engineering, and architectural design. What makes it even more impressive is that it was built without any of the mathematical tools or computational methods that modern engineers consider essential. The dome's construction required solving multiple engineering challenges simultaneously. The concrete had to be strong enough to support its own enormous weight while spanning 142 feet without any internal supports. The structure had to be stable during construction before the concrete had fully cured, and the entire building had to withstand seismic activity in a region prone to earthquakes. Roman engineers solved these problems through ingenious design and materials engineering. The concrete composition varies throughout the dome, with heavier aggregates, pieces of stone and brick, used in the lower sections and lighter materials like pumice used near the top. This reduces the overall weight while maintaining structural integrity. The dome also features a complex pattern of internal voids and chambers that reduce weight while actually strengthening the structure. These internal spaces weren't visible from inside or outside the building, suggesting that Roman engineers understood structural principles that wouldn't be formally described by engineering science for more than 1,000 years. Temperature control was another consideration. The massive thermal mass of the concrete dome means that the interior temperature of the Pantheon remains relatively constant throughout the year. The famous oculus, the circular opening at the top of the dome, provides ventilation and lighting while also serving as a thermal relief valve that prevents the dome from cracking due to temperature changes. The precision of the Pantheon's construction is remarkable. The dome is perfectly spherical, with the interior surface forming part of a sphere that, if completed, would exactly touch the floor. This geometric perfection required sophisticated surveying and construction techniques that ensured every part of the dome was built to precise specifications. Recent scientific analysis has revealed even more sophistication in Roman concrete technology. The volcanic ash used in Roman concrete contains minerals that continue to react chemically for decades after construction, gradually strengthening the matrix. Modern concrete reaches its maximum strength within days or weeks of being poured, then slowly deteriorates. Roman concrete continues to strengthen for years. The Romans also developed different concrete formulations for different applications. Underwater concrete used a different mix that could set and cure while submerged. High-strength concrete for major architectural elements included specific aggregates and additives. Decorative concrete could be colored or textured to achieve various visual effects. Harbor construction showcased another remarkable property of Roman concrete: its resistance to seawater. While modern concrete deteriorates rapidly in marine environments due to salt corrosion, Roman concrete actually becomes stronger when exposed to seawater. The volcanic ash in the mixture reacts with seawater to form additional binding compounds that increase durability. This seawater resistance allowed the Romans to build massive harbor installations that have survived nearly 2,000 years of constant wave action and salt exposure. The harbor at Caesarea, built by Herod around 25 BC, featured massive concrete breakwaters that protected ships from Mediterranean storms. These structures remain largely intact today, while modern concrete seawalls require frequent maintenance and replacement. The speed of Roman construction was also impressive. The Pantheon, despite its complexity and massive scale, was built in just a few years. This rapid construction was possible because Roman concrete could be poured continuously, unlike stone construction that required careful fitting of individual blocks. Large teams of workers could work simultaneously on different parts of the structure. Quality control in Roman concrete production required sophisticated understanding of materials and chemistry. The volcanic ash had to be sourced from specific locations and processed to exact specifications. Lime production required precise temperature control and timing. The mixing process had to achieve uniform distribution of all components while maintaining proper water content. The Romans developed specialized tools and techniques for concrete construction that wouldn't be matched for centuries. They used wooden forms to shape complex curved surfaces, bronze tools for finishing work, and even primitive rebar made from bronze rods to reinforce critical areas. These construction methods allowed them to build structures that were impossible with any other technology. Architectural innovations made possible by Roman concrete included previously impossible structural elements. The dome was just one example. Romans also built massive barrel vaults, complex intersecting arches, and multi-story buildings with floor spans that wouldn't be achieved again until the development of steel construction. The economic impact of concrete technology was enormous. Roman concrete allowed faster, cheaper construction of everything from aqueducts to apartment buildings. This construction efficiency helped support the rapid expansion of Roman cities and infrastructure throughout the empire. The technology was so successful that Romans built concrete structures from Britain to North Africa to the Middle East. But then, something remarkable happened. The technology was lost. As the Roman Empire declined and fell, the knowledge of how to make proper Roman concrete disappeared. The specific sources of volcanic ash were forgotten, the precise mixing ratios were lost, and the skilled craftsmen who understood the technology died without passing on their knowledge. Medieval builders reverted to stone and brick construction, unable to replicate the concrete achievements of their predecessors. It wasn't until the 18th century that Europeans began redeveloping concrete technology, and even then, early modern concrete was inferior to what the Romans had achieved centuries earlier. This loss of knowledge illustrates how fragile technological advancement can be. The Romans developed concrete not through scientific research, but through practical experimentation and refinement over generations. When the social and economic systems that supported this knowledge collapsed, the technology disappeared with them. Modern attempts to recreate authentic Roman concrete have met with mixed success. While we now understand the basic ingredients and chemical processes involved, replicating the exact properties of Roman concrete remains challenging. The specific volcanic ash sources used by the Romans have different compositions than modern alternatives, and the traditional lime production methods created slightly different chemical properties. Contemporary research into Roman concrete has inspired new approaches to sustainable construction. The self-healing properties of Roman concrete could revolutionize modern building if successfully replicated. Scientists are experimenting with bioconcrete that uses bacteria to heal cracks, inspired by the limestone clasts in Roman formulations. The environmental benefits of Roman-style concrete are also significant. Modern concrete production is responsible for about 8% of global carbon dioxide emissions, largely due to the energy-intensive process of making Portland cement. Roman concrete used much less energy to produce and created a more durable product that lasted longer. Earthquake resistance is another area where Roman concrete excels. The flexible nature of Roman concrete allows it to absorb seismic energy without catastrophic failure. Many Roman structures in earthquake-prone regions have survived tremors that would devastate modern concrete buildings. The Pantheon itself has survived numerous earthquakes, including major tremors in 847 AD and 1349 AD that damaged other Roman buildings. The dome's unique design and materials allow it to flex and move during seismic events without cracking or collapsing. This earthquake resistance wasn't accidental. Roman engineers in seismically active regions developed specific techniques for earthquake-resistant construction. As we stand in the Pantheon today, looking up at the oculus and the magnificent dome that surrounds it, we're witnessing a technology that surpassed anything that came after it for more than 1,000 years. The Romans achieved something that modern engineers are still trying to fully understand and replicate. The concrete dome above our heads has weathered barbarian invasions, medieval neglect, Renaissance renovations, and modern pollution. It has survived longer than the empire that built it, longer than the religion it was designed to serve, longer than most civilizations in human history, and it shows no signs of deteriorating anytime soon. Roman concrete represents more than just a building material. It represents a way of thinking about construction and engineering that prioritized longevity over short-term costs. Roman builders expected their structures to last centuries, and they designed them accordingly. This long-term thinking resulted in infrastructure that continued serving communities long after the original builders were forgotten. The rediscovery and study of Roman concrete technology offers hope for more sustainable construction in the future. By understanding how ancient engineers achieved such remarkable durability with relatively simple materials, we might develop new approaches to building that are both environmentally responsible and incredibly long-lasting. Our final journey takes us east, to the great forges of medieval Damascus and the workshops of master smiths who created the most legendary steel in human history. Damascus steel blades were so sharp they could slice through silk scarves floating in the air, so strong they could chop through European swords without chipping, and so beautiful that each blade displayed unique patterns that looked like flowing water frozen in metal. The reputation of Damascus steel spread across the medieval world like wildfire. Crusader knights spoke in hushed tones of Saracen swords that could cut through their finest armor as if it were cloth. European merchants paid fortunes for Damascus blades, which became symbols of ultimate prestige and power. Kings and emperors collected these weapons like precious jewels, and master swordsmiths from Damascus commanded respect that bordered on reverence. But here's the remarkable thing about Damascus steel. We have no idea how it was made. The technology was lost around 1700 AD, and despite 3 centuries of research using everything from electron microscopes to mass spectrometry, modern science has been unable to recreate authentic Damascus steel. We can make excellent steel today, but we cannot make Damascus steel. The story begins in ancient India, in the regions that are now Sri Lanka and southern India, where smiths discovered how to create a type of steel they called woots. This wasn't ordinary steel. It was a crucible steel made using a process that created unique internal structures that wouldn't be understood by metallurgy for over 1,000 years. Woot steel ingots were traded along the Silk Road to Damascus, where Syrian smiths developed the forging techniques that transformed the raw material into the legendary Damascus blades. The combination of Indian metallurgy and Syrian craftsmanship created a technology that represented the pinnacle of medieval engineering. What made Damascus steel so extraordinary? The answer lies in its internal structure, which modern analysis has revealed to be incredibly complex. Damascus steel contains carbon nanotubes, microscopic structures that wouldn't be officially discovered by science until the 1990s. These nanotubes, along with other microscopic features, gave Damascus steel properties that modern metallurgy still struggles to achieve. The strength of Damascus steel came from its unique microstructure. The steel contained bands of different carbon content, creating layers of hard and soft metal that were folded and twisted together during forging. This process created a composite material that combined the best properties of both high-carbon and low-carbon steel. incredible hardness for a sharp edge, and flexibility to prevent breaking. But strength was only part of the Damascus steel mystery. The blades displayed distinctive surface patterns that looked like flowing water, wood grain, or even ladder-like steps. These patterns weren't decorative additions. They were natural features that emerged from the steel's internal structure during forging. Each blade had a unique pattern that couldn't be duplicated, making every Damascus sword a one-of-a-kind work of art. The sharpness of Damascus blades was legendary and appears to have been genuine. Historical accounts describe Damascus swords cutting through European blades, slicing silk scarves in midair, and maintaining their edges through battles that would dull ordinary weapons. Modern tests on surviving Damascus blades have confirmed that they can achieve edge geometries and cutting performance that exceed most modern knives. The forging process that created Damascus steel was incredibly complex and required master-level skill. The smith had to heat the wootz steel to exact temperatures, work it at precise intervals, and control the cooling process with extraordinary precision. A tiny mistake in timing or temperature could ruin weeks of work and destroy valuable raw materials. Syrian smiths guarded their techniques jealously, passing knowledge from master to apprentice through generations. The process was never written down in detail, relying instead on hands-on training and closely held trade secrets. This oral tradition meant that when the last mastersmiths died without properly training successors, the knowledge disappeared forever. The end of Damascus steel production around 1700 AD was probably caused by multiple factors working together. The sources of wootz steel in India became exhausted or were disrupted by political changes. The guild system that preserved smithing knowledge began to break down, and the introduction of firearms reduced demand for traditional bladed weapons. Modern attempts to recreate Damascus steel have involved some of the world's leading metallurgists and material scientists. They've analyzed surviving blades using every tool available to modern science: electron microscopy, X-ray crystallography, mass spectrometry, and computer modeling. These studies have revealed the incredible complexity of Damascus steel's internal structure, but understanding how it was made remains elusive. The carbon nanotube discovery was particularly shocking to modern scientists. These structures, which modern science considers cutting-edge nanotechnology, were being produced in medieval forges using techniques that seemed impossible. The smiths somehow created conditions that allowed carbon atoms to self-assemble into these incredibly strong microscopic tubes. Contemporary metallurgists have tried to recreate Damascus steel using modern furnaces, computer-controlled heating, and precisely measured alloy compositions. Some efforts have come close to matching certain properties of authentic Damascus steel, but none have successfully replicated all the characteristics: the distinctive patterns, the exceptional sharpness, the legendary strength, and the unique microstructure. The mystery deepens when we consider that medieval smiths achieved this breakthrough without understanding the science behind their work. They had no knowledge of metallurgy, crystallography, or material science. They couldn't see the microscopic structures they were creating or measure the chemical compositions they were working with. Yet somehow, through trial and error and accumulated experience, they developed a technology that modern science still finds impressive. The economic value of Damascus steel was enormous. A single blade could cost as much as a small farm or a year's wages for a skilled craftsman. The steel was so valuable that broken Damascus blades were often reforged rather than discarded, and even small pieces were treasured and incorporated into new weapons. Trade networks centered around Damascus steel connected Europe, Asia, and the Middle East. European merchants made fortunes importing Damascus blades, while Indian producers of wootz steel prospered from exports. The technology created an international industry that lasted for over 1,000 years. The cultural impact of Damascus steel extended far beyond its practical applications. The blades became symbols of power, skill, and prestige across multiple cultures. Literature and folklore from medieval Europe to ancient India contain references to magical swords that could cut through anything, many of which were probably inspired by Damascus steel weapons. Religious significance was also attached to Damascus steel blades. Many cultures believed that the distinctive patterns held spiritual meaning, or that the forging process imbued the blades with supernatural properties. Some Damascus swords were inscribed with prayers, verses, or protective symbols, combining metallurgical mastery with spiritual beliefs. The loss of Damascus steel technology represents one of history's greatest technological reversals. This wasn't simply a matter of one technique being replaced by a better one. Damascus steel was superior to anything that came after it for centuries. The technology was lost not because it was superseded, but because the knowledge couldn't be preserved through periods of social and economic disruption. Apprenticeship systems that relied on oral tradition were particularly vulnerable to this kind of knowledge loss. When master smiths died in wars, plagues, or political upheavals before fully training their successors, entire technical traditions could disappear. This happened repeatedly throughout history, representing an enormous loss of human knowledge and capability. Modern research into Damascus steel has contributed to advances in materials science and nanotechnology. Understanding how medieval smiths accidentally created carbon nanotubes has inspired new approaches to manufacturing these valuable structures. The study of Damascus steel's unique properties has also influenced the development of modern composite materials and advanced alloys. 3D printing and computer modeling are opening new possibilities for recreating Damascus steel. Some researchers are using additive manufacturing to build steel structures layer by layer, potentially allowing precise control over internal patterns and compositions. Others are using artificial intelligence to analyze the relationships between forging techniques and final properties. The environmental implications of Damascus steel technology are also significant. The medieval process used relatively little energy compared to modern steel production, relying primarily on charcoal furnaces and human labor. If the techniques could be recreated and scaled up, they might offer more sustainable approaches to manufacturing high-performance metals. Reverse engineering efforts continue today, with metallurgists around the world working to unlock the secrets of Damascus steel. Each surviving blade provides clues about composition, structure, and manufacturing techniques. Advanced analysis methods that didn't exist even a decade ago are revealing new details about how these remarkable weapons were made. The quest to recreate Damascus steel represents more than just academic curiosity or technological challenge. It's an attempt to recover lost human knowledge and capability, to bridge the gap between ancient wisdom and modern science. Success would represent not just a metallurgical achievement, but a reconnection with our technological heritage. Some modern smiths claim to have recreated Damascus steel using traditional methods and carefully researched techniques. While these efforts produce beautiful and functional blades with distinctive patterns, metallurgical analysis usually reveals differences from authentic historical Damascus steel. The patterns may look similar, but the underlying structure often lacks the complex features found in genuine examples. The debate over modern Damascus steel illustrates the difficulty of verifying historical technologies. Without detailed documentation of original techniques, it's nearly impossible to prove that a modern recreation is truly authentic. Even if a modern blade matches all the measurable properties of historical Damascus steel, we can't be certain that it was made using the same methods. As we conclude our exploration of Damascus steel, we're left with a humbling realization. Medieval smiths, working with simple tools and basic furnaces, achieved something that modern science still finds remarkable. They created a material that combined properties we now know shouldn't exist together, using techniques that produce structures we've only recently learned to appreciate. The story of Damascus steel reminds us that human ingenuity and accumulated knowledge can achieve extraordinary things, even without formal scientific understanding. It also warns us about how easily such knowledge can be lost if we don't take care to preserve and transmit it properly. Standing in a museum today, looking at a Damascus blade that gleams with its characteristic watered steel pattern, we're seeing evidence of human achievement that transcends its historical period. We're looking at technology that was so advanced for its time that we're still trying to understand it centuries later. As our journey through ancient engineering marvels comes to an end, we're left with a profound and somewhat unsettling realization. Our ancestors accomplished things that we, with all our modern technology and scientific understanding, struggle to comprehend or replicate. The Great Pyramid of Giza stands as a monument to precision and scale that modern construction has rarely matched. Built 4,500 years ago using Bronze Age tools, it achieved tolerances and alignments that would challenge contemporary engineers. The Japanese pyramid experiment of 1978 demonstrated that even with modern backup equipment, recreating ancient Egyptian construction methods is extraordinarily difficult. Roman concrete technology produced structures that have outlasted the civilization that created them. The Pantheon's dome has stood for nearly 2,000 years without major repairs, while modern concrete buildings require constant maintenance and are designed to last only decades. The self-healing properties of Roman concrete represent a sophistication in material science that we're only beginning to understand and attempt to replicate. Damascus steel combined properties that modern metallurgy considers contradictory. Extreme hardness with flexibility, razor sharpness with durability, and strength with workability. The discovery of carbon nanotubes in Damascus steel shocked scientists who realized that medieval smiths were accidentally creating cutting-edge nanotechnology using simple forges and hand tools. What unites these three achievements is their combination of practical functionality with levels of sophistication that exceeded anything that came after them for centuries or even millennia. These weren't primitive first attempts that were later improved upon. They were technological peaks that weren't surpassed until the industrial age, and in some cases, haven't been surpassed at all. The loss of these technologies illustrates how fragile human knowledge can be. Damascus steel production ended not because better techniques were developed, but because the knowledge couldn't survive social and economic disruption. Roman concrete techniques were forgotten when the empire fell, forcing medieval builders to start over with inferior methods. Even pyramid construction methods remain mysterious despite intensive study by modern archaeologists and engineers. These ancient achievements challenge our assumptions about technological progress. We tend to think of human development as a steady upward climb, with each generation building upon the knowledge of previous ones. But history shows us that knowledge can be lost as easily as it's gained, and that technological sophistication doesn't always correlate with historical period. The engineering principles demonstrated in these ancient projects often required understanding that wouldn't be formally described by science for thousands of years. Egyptian pyramid builders understood structural engineering principles that weren't codified until the modern era. Roman engineers used material science concepts that contemporary researchers are still studying. Damascus steelsmiths created nanotechnology without knowing what atoms were. This suggests that practical knowledge and theoretical understanding can develop independently. Ancient craftsmen and engineers developed sophisticated techniques through trial and error, accumulated experience, and careful observation, even without the mathematical and scientific frameworks that modern engineers consider essential. The precision achieved in these ancient projects is particularly impressive given the tools and methods available. Modern engineers rely on computer modeling, precision instruments, and standardized materials to achieve accuracy. Ancient builders achieved comparable or superior precision using measuring rods, plumb lines, and accumulated experience passed down through generations. The organizational capabilities required for these projects were also remarkable. Building the Great Pyramid required coordinating thousands of workers, managing complex supply chains, and maintaining quality control over decades-long construction periods. This level of project management would be challenging even with modern communication and organizational tools. The durability of these ancient achievements speaks to a different philosophy of construction than what prevails today. Ancient builders expected their work to last centuries or millennia, and they designed accordingly. Modern construction often prioritizes short-term cost savings over long-term durability, resulting in structures that require frequent maintenance or replacement. Environmental considerations also played a role in ancient engineering success. Roman concrete used local volcanic ash that improved performance while reducing transportation costs. Egyptian pyramid builders used locally quarried limestone for most of the structure, importing granite only for critical elements. Damascus steel production utilized regional raw materials and energy-efficient forging techniques. The loss of these technologies has had lasting consequences for human development. If Roman concrete techniques had been preserved, medieval builders could have constructed more durable infrastructure. If Damascus steel methods had survived, metallurgy might have advanced more quickly. If pyramid construction methods were understood, modern engineering might benefit from ancient insights into precision construction. Contemporary efforts to understand and recreate these ancient technologies are yielding new insights into material science, engineering principles, and construction methods. Studying Roman concrete has inspired research into self-healing materials and sustainable construction. Analysis of Damascus steel has contributed to nanotechnology development. Investigation of pyramid construction has revealed new approaches to precision engineering. But these modern research efforts also highlight how much we still don't know about our own technological heritage. Despite decades of study using the most advanced analytical tools available, we still can't fully explain how these ancient achievements were accomplished. The gap between our theoretical understanding and the practical knowledge of ancient craftsmen remains frustratingly large. The cultural and social contexts that enabled these technological achievements are as important as the technical knowledge itself. The Egyptian Old Kingdom, Roman Empire, and medieval Islamic world all fostered environments where long-term thinking, skilled craftsmanship, and technological innovation could flourish. These societies invested resources in projects that wouldn't provide immediate returns but would benefit future generations. The apprenticeship systems that preserved and transmitted technical knowledge were crucial to these achievements. Master craftsmen spent decades perfecting their skills and passing knowledge to carefully selected students. This human chain of knowledge transmission was more effective than written documentation for complex, hands-on techniques, but it was also more vulnerable to disruption. Religious and cultural motivations often drove these engineering projects beyond what pure practicality would justify. The Great Pyramid was built as a pharaoh's tomb and symbol of divine power. The pantheon served as a temple to all the gods. Damascus steel blades often carried religious inscriptions and spiritual significance. This higher purpose may have inspired the extraordinary effort and attention to detail that made these projects so remarkable. The economics of ancient engineering also differed significantly from modern practices. Labor was often abundant and relatively inexpensive, while materials and transportation were costly. This economic structure encouraged labor-intensive techniques that maximize the value of expensive materials, often resulting in more durable and precisely crafted products. Quality control in ancient projects relied heavily on individual skill and pride in craftsmanship rather than standardized testing and measurement. Master builders and smiths staked their reputations on the quality of their work, creating powerful incentives for excellence that may have been more effective than modern quality assurance systems. The holistic approach to engineering found in these ancient projects is worth noting. Modern engineering tends to specialize in narrow disciplines, but ancient builders had to integrate structural, materials, environmental, and aesthetic considerations simultaneously. This integrated thinking may have contributed to the remarkable success of their projects. Climate and environmental factors played important roles in these ancient achievements. The dry climate of Egypt helped preserve pyramid construction details that would have been lost in wetter environments. The volcanic ash available to Roman builders was crucial to their concrete technology. The specific ores and climate conditions of the Indian subcontinent were essential for wood steel production. The preservation of knowledge across generations required stable social institutions and cultural continuity. When these supporting structures collapsed due to war, disease, or economic disruption, technical knowledge often disappeared with them. This vulnerability of oral traditions and apprenticeship systems to social upheaval represents a significant risk to technological development. Modern attempts to recreate these ancient technologies often focus on replicating the final products rather than understanding the underlying processes and knowledge systems. True recreation would require not just matching the physical properties of ancient materials, but understanding the cultural, economic, and social contexts that made their development possible. The study of ancient engineering achievements offers valuable lessons for contemporary technology development. The emphasis on durability, the integration of multiple engineering disciplines, the attention to environmental factors, and the long-term thinking that characterize these projects could inform modern approaches to sustainable development and infrastructure planning. As we face contemporary challenges like climate change, resource depletion, and the need for more sustainable technologies, ancient engineering wisdom becomes increasingly relevant. The Romans' approach to concrete that becomes stronger over time, the Egyptians' precision in construction that minimizes waste, and the Damascus smiths' efficient use of energy and materials all offer insights for modern innovation. The humility required to acknowledge that ancient peoples achieved things we still don't fully understand is an important corrective to technological arrogance. Recognizing the sophistication of past achievements can inspire greater respect for traditional knowledge and more careful consideration of what we might be losing as technologies become obsolete. Perhaps most importantly, these ancient engineering marvels remind us that human ingenuity, creativity, and determination can accomplish extraordinary things regardless of the technological tools available. The builders of the pyramids, the engineers of the Pantheon, and the smiths of Damascus didn't have computers, power tools, or scientific instruments, but they had vision, skill, and the persistence to pursue perfection. As you drift off to sleep tonight, consider the remarkable legacy of human engineering achievement that surrounds us. Every time you see a building that has stood for decades, drive across a bridge that spans a wide river, or use a tool that performs its function perfectly, You're benefiting from thousands of years of accumulated knowledge and innovation. The ancient engineers whose work we've explored tonight were no different from modern builders in their fundamental goals. They wanted to create things that worked, that lasted, and that served human needs. They succeeded so well that their achievements still inspire wonder and respect nearly 2,000 years later. Sleep peacefully, knowing that human creativity and determination have overcome seemingly impossible challenges throughout history. The pyramids still stand. The Pantheon's dome still soars overhead, and somewhere in a museum, a Damascus blade still gleams with its mysterious watered steel pattern, all testament to the extraordinary things humans can accomplish when they combine knowledge, skill, and an unwavering commitment to excellence. Sweet dreams, and may you rest well under the protection of structures built by engineers who understood that true achievement isn't measured in years or decades, but in centuries and millennia. Their work endures not just in stone and steel, but in the continuing human quest to build better, reach higher, and create things that will outlast their creators.